Well, hello friends. Welcome back to the show. Today we are taking a look at the HXP CTF. So for the second year in a row, Serenity was part of the HXP Capture the Flag competition where people try to break into the system and get local root access. And you can read this whole report here on hxp.io. I'll put a link in the video description. But basically today we're going to take a look at one of the exploits that came out of this competition, which is listed here. And then it also mentions that there was one team that managed to break into the system, which is a huge improvement compared to last year, where they had 6 teams that broke into the system. So kind of a testament to our improvements in the security department over the last year. Which have been many, but also a wake-up call to remember that we're not really where we want to be with security. Obviously, it would be cool to make even more improvements in the next year. Anyway, so this particular situation here that that they've exploited is a race condition in the exec syscall. So let's just jump right over to exec and we can take a look at the problem. So let's see. Okay, so here is the do exec function, which is part of the exec mechanism. And the problem is that here we load the new executable and then a bit further down, we actually change the UID and the GID of the process if we are executing a set UID program. So, of course, set UID programs is something like bin password or bin su or bin ping, right? Like something that needs to run with elevated privileges in order to perform some restricted task. So when we exec such a program, we load the program and then a bit later we switch the UID. And the thing that you can exploit here is this time window in between, because you can actually attach to the process with ptrace and poke around with the memory of the process remotely from another process while we are right here in this time window. And let's just compile this exploit here. The way that they extend this time window in the exploit to like make it larger to get a higher chance of winning this race is that one of the things that we do here in this time window is that we clear the list of unveiled paths in the process we're execing in. So if you have a huge list of unveiled paths, this might take a bit longer than a short list. So the exploit here, as we'll see in a moment, they take advantage of this by just unveiling a huge number of paths, which causes this thing here to be slow, which makes it pretty easy to hit this time window. But let's see, let's just call this hacks. And let me see if I can just lift it in here. And will this compile just as it is? Maybe that would be nice. Let's see, what was that? Child and parent. Okay, so it's not completely conforming to our coding style, which is not something I expect from third-party exploits, but still, in order to compile it with our own build system, we have to at least fix the warnings. So, okay, here we go. And then, so basically what they do here is that they unveil all of these paths. And then after that, they do an exec. So let's see, let's take a look. So it didn't work this time, by the way. At least it doesn't look like it because I'm not root, right? Yeah. Yeah, so let's look at the exploit here. So what they do in main is that this stuff here is just if you're participating in their CTF. So the object of the CTF was to extract some string from secondary hard drive, but we can just ignore that part and focus on the exploitation part because that's what's interesting here. Yeah, so what they do is, let's see, they prepare some shellcode, blah, 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 and then they fork, and then ass, and then they have a parent and a child function. So let's go look at the parent function, or actually rather, let's go look at the child function, because that's where the unveil happens. Right, so if you look here, they're constructing a whole bunch of paths, temp YOLO dash number, and then tells the kernel to unveil that path. And that's what fills up the process list of unveiled paths. So then after they've done that, then the child is ready, and they wait for the parent to attach to this process. And we do that, I guess, by waiting for the parent to ptrace poke into the memory space of the child. And then we do the exec of a setuid binary, and then I guess during that exec is when the parent is expected to attach and perform some shenanigans. So let's look at parent. So what they do is waiting for ready. Wait, what is ready anyway? Oh, forgive me. That's just a shared piece of shared memory. Okay, so they're just using a shared memory to signal each other. Okay, that's fine. Okay, so the parent waits for the child to wake up, and then it will attach to the child via ptrace and then poke into his memory. So basically what he does is that he attaches after we've loaded the password program, but before we have switched the UID and the GID of the password program to root. And because of that, attach is possible. Normally, you shouldn't be allowed to attach to a privileged process running as root if I'm not root, right? But because of the race window, the attach succeeds, and then we can actually overwrite in the child process the piece of code that's about to be executed. So I think that's essentially what happens, and then after that, it's just first it's just trying to figure out if it's actually possible to overwrite the memory, blah blah blah. And then where do we dump the shellcode? Oh, I guess here is where we write the shellcode into the child process. Okay, and then we have these hard-coded addresses here. So this, I guess, is the ELF entry point of the dynamic loader, and this must be the entry point to the exec function in libc, so also in the loader. So let's take a look at our loader first of all here. So that would be userland dynamic loader.so. Okay, so our entry is 1BA6, which is 1BA6, and then we have this issue here actually that this is hard-coded. We always load the dynamic loader at the same address, which is, yeah, to do. This should be randomized for ASLR. It's pretty unfortunate that we always load the dynamic loader at the same address. I feel like we could, at the very least, irritate exploitation attempts here by randomizing this. of course, we are 32-bit right now, so there's limited space for randomization, but even so, you could thwart some amount of exploitation by randomizing this offset. It seems worth doing. Anyway, so let's see. So then we have the exec entry point. Let's just find that, because I bet it's not exactly the same in his example code here that I have locally compiled. So let's just grab for exec 32.7 AD, 32.7. Yeah, so we got to fix that. 32.7 AD, right? Yes. Okay. Let's see if this actually works. It might be that my machine is too fast for this, so let's run without KVM. Yeah, I'll just turn off KVM support in QEMU, and that will make the whole machine run like significantly slower, which will widen that race window even more. We'll take a moment. It'll take quite a few moments, but in the meantime, I guess we can think about what we want to do here to protect against this. So let me just switch my IDE to kernel mode. Okay, so the first and most obvious thing that comes to mind is that we would switch the UID before loading the executable, because loading in this case, it really just means creating the new sort of memory layout of the program. And that's something that can fail. So we would need to recover and reset the old UID in case that fails. But if we look at ptrace, let's see. This is ptrace. Okay, so when we enter into ptrace, we have a check right here. Disallow tracing set UID processes. So if you try to ptrace a process that you are not supposed to, you'll get an eAccess error. But this check here is exactly the check that's failing right now because we are just attaching at a terrible time. So if we move this stuff before we load, oh, look at that. It ran and it worked and we are root. Yeah, so you can see the problem. And that's a very clever exploit. I'm really happy that that they reached out and we learned about this issue so that we can fix it. And it's been a while since we looked at stuff like this, and it's very, very exciting. And I'm just now remembering how much fun this is. So anyway, what are they saying here? ASLR has very recently been enabled since dynamic linking is now the default. Luckily not for the dynamic linker, indeed, which always ends up at 08 fajillion. Yeah, that's very unlucky. We don't actually have proper ASLR. I think that's maybe a little misunderstanding, but there's a slight inconsistency to the way shared libraries are loaded, so they're harder to predict, but the dynamic loader is always at exactly the same place, which is, of course, very easy to take advantage of here. So maybe we should do something about that today as well. Maybe we can do something small about that. But let's see. So let's hoist this stuff. Let's see. Say note. We switch the UID GID early. Switch credentials early. or before altering the memory layout of the process. This ensures that ptrace access control takes credentials into account, takes the right. So this doesn't feel like a complete solution. Let's say fix me this. Perhaps this still feels rickety. Perhaps it would be best to simply block ptrace clients until we're ready to be traced, or reject them with EPER. Yeah, I'm not sure exactly what we should be doing, but we can at the very least cover up this issue here. So let's start with that, and then we'll make an armed scope guard. Let's see, so old UID is MUID. Wait, what are we setting here? EUID and SUID. Okay, so EUID. Let's do all of these fellas. Okay, and then we'll make a credential restoration guard. Yeah, this feels kind of awkward, but it should at least protect us against this particular problem. So let's see. So we'll run this. Basically, the armed scope guard is something that will be executed when you exit the scope. So, but you can disarm it, and then it will no longer execute when you exit the scope. So basically, here, if the load succeeds, then we will cred restore guard, disarm. Okay, and let's we can commit to the new credentials at this point. Okay. Yeah, so then what happens? Also, why is unveil so slow when you're running it so many times? Unveil, unveil, unveil. What is it even doing? Oh, right. Okay, so it's iterating over all of the currently already unveiled paths and looking if you're just updating an existing one. So let's just patch this loop out just to make the exploit run a little faster. This is just making unveil always succeed, even if you're unveiling a previously unveiled path. We'll just let it succeed faster. Yeah, that's a lot less painful to wait for. So e-access, this is exactly what we wanted. It rejected it because we've set the credentials early. I guess we can just try to run the exploit a few times, but we should be guarded against this right now. So yeah, this doesn't feel like a systematic solution so much as like kind of a hot fix, but even so, I don't dislike it. It seems better to commit to this early, but I really dislike the fact that ptrace can connect to this program at all while we're in exec. So that's probably something that we should look at, but that will require a bit more sort of high-level work and a more high-level investigation. So for today, let's simply do this. I think this is okay. So I do think we have prevented the exploit. Yeah. And what happens if we go back to the way things were? And try the exploit again, just to be sure. Just to be sure that I didn't screw it up with those unveil changes, because that would be stupid. Yeah, no, we're root here. Okay, right, so that's pretty interesting. This is really fun. Like, I kind of forgot how much fun this is, but I'm glad that we are remembering. So, super shout outs to the HXP people and Lawrence, who put this particular challenge together and made the exploit. It's very, very awesome Christmas present. I'm very happy to to see this, and I hope to hear from the team that was successful in hacking Serenity and seeing what bug they exploited, so we can take a look at that as well. But I guess we'll see if they announce it. Hopefully they do. If you're not familiar, the Serenity operating system does have a bug bounty program that you can find on serenityos.org/bounty, where I will pay out $5 for exploitable bugs in these categories. You can read the whole rule set here, and it obviously it's a low budget program, but I like to take security seriously, so doing what we can here. Anyway, so I think we can commit to this patch. Let's see. Oh, that's an accidental change. We don't want that. Ignore that. Okay, so kernel. What do we say? Switch or activate SUID, SJD credentials earlier, and says exec. Switch on the new credentials before loading the new executable into memory. This ensures that attempt to ptrace the program and messing with the code that's about to run with elevated privileges, or let's see, ptrace the program from an unprivileged process will fail. Yeah, and then trying to remember what I'm just looking for the commit message from the last year's CTF. Oh man, I don't remember what they were called. Okay, well, thanks to or this fixes, covers, this exploit, this covers the bug was exploited in one bug that was exploited in the 2020 HXP CTF. Yeah. And then let's take a look at that hard-coded offset. So what if we were to just mess with that a little bit? Does it have to load there? Like, what if I just say like A instead or something? I feel like that should still just work, no? Yeah, everything still runs. So usually land dynamic loader. So there's nothing that says that it has to be loaded at that specific address. So why don't we just do something here? Like, we'll start it somewhere, like at, I mean, we can start it where it was and then add some number to it, right? Plus get random, get good random. Let's just get a, what happens if we get good random? We can just, okay, wait, hold on here. Randomized better, let's say, but we can still add an annoying little bit of random noise here, just to make it harder for the next person who tries stuff. So let's see, what if we do something like that and then times page size? So then what would we get? 256 by 496. So then it's a megabyte range up and down it will end up in. I guess we can widen that a little bit. What happens if we spread it out that much? So then loading dynamic loader at I'm actually curious, will this work? It totally works. Okay. Yeah, so now we are randomizing where we load the dynamic linker or dynamic loader, which should totally break this exploit, even if you, I mean, you can probably still get around it if you can guess where it will be loaded, but that immediately becomes significantly harder, I would think. So that's positive. But I'm sure that we can do something better and smarter here. This is just very like me just throwing something together. I'm sure this can be randomized even better. Yeah, because we're not like, probably not using the full range available to us, obviously, and there might be some other considerations, but still, that is really sweet. So let me turn on KVM again so that we can boot a bit faster, because it's a bit annoying how slow that it boots. Yeah, there we go. And stuff still works just fine. It's just that oh, look at that. It crashes the well, now it crashes the kernel instead. So we're crashing with an assertion in ptrace poke. So let's see why did we crash there? I guess because it was expecting when it was using the hard-coded address, then it had a known address that always worked. So we get here and we assert that we always find a region containing this address, but it seems perfectly reasonable that a remote ptrace client would try to poke at an invalid address. And if so, I feel like we should just shouldn't we just e-inval them? Or e-fault, rather? What did they normally say? E-fault. There was an attempt to read from or write to an invalid area in the tracer's or the tracee's memory. Indeed. That seems pretty reasonable to me, that we would just e-fault if you try to poke at an invalid address. Yeah. We should just allow that. Okay. And of course this doesn't work at all because we have now protected ourselves doubly. Very cool. So let's start with the ptrace poke fix here. So kernel ptrace should not assert on poke in invalid memory region or in non-mapped tracee memory. Yeah, because why would we? And then put the randomize where we put the dynamic loader. Randomize memory location of the dynamic loader. This should make it a little bit harder for those who would mess with the the instructions inside. For those who would mess with the mess with our loader. Yes, it should make it a little bit harder. Okay, so I think those are the mitigations that we're going to make here today. If you have any other suggestions for mitigations, or if you noticed me making some stupid mistake or something here, please let me know. I am super interested in making the system more secure, more robust, obviously, and I think this sort of thing is super interesting. And obviously we have more bugs, and I'm very happy that this was found. I think we can do a lot more to improve all of the code that we've looked at today, but at least we have patched up these exposed problems. Anyways, I think we're gonna end the video here. So if you made it this far, then I thank you for watching, for hanging out. And again, special thank you to the HXP folks for including us in the Capture the Flag, and for doing this awesome write-up with the exploit and everything so that we can fix it. And I hope that we can do this again sometime. Yeah, thanks for hanging out. I'll see you next time. Bye.